Ready for the k-means algorithm? The k-means algorithm is an example of unsupervised learning algorithm. As we said in lesson 1, unsupervised learning is that part of machine learning that deals with the discovery of patterns in the data. Our goal is not immediately to predict the values of a given variable of a target, but rather to understand the structure of our dataset. The k-means algorithm is an example of clustering algorithm. Our goal is to find clusters, that is to say, groups of observations, people, things that are homogeneous with respect to one or more characteristics. For a bank, an unsupervised learning algorithm like the k-means can be used to cluster the customers. Why? Because they want to better understand their customers. They want to group their customers in terms, for example, of banking needs so that they can provide a better service, or in terms of other characteristics that can be useful in order to develop different offers to the different type of customers. Or in the Basel framework, the bank could be interested in grouping the different customers in terms of creditworthiness. So the goal of the k-means algorithm is to cluster observations. Now imagine, as a starting point, that we are in a two-dimensional framework. That is to say, we have a certain number of customers, a certain number of observations, and for each customer, for each observation, we have two variables, two features that we can use as instruments to cluster the observations. The idea is that using the information in the features, we want to build a certain number of groups, say two. And what is interesting in the k-means algorithm is that we start by not knowing, or at least it is not necessary to know what the group will be. The interpretation of the groups will come after. So our job will be to try to understand what the groups actually represent. So if you want, our hypothetical data set in which we have observations for which we have two features can be represented as in the graph here. So if the information in the features we have is useful, so these features can actually be used to discriminate and to group the different observations. This is not always the case, so having the right data is always fundamental. In statistics, in machine learning, in data science, as you want to call it, the quality of data is fundamental. But this is something that we will treat later on also in other parts of the course. But remember, the quality of the data is fundamental, in particular in machine learning, because we learn from the data. So our intervention is limited with respect to other approaches. Okay, what happens is that if the quality of the data is okay and the features are meaningful to us, the k-means algorithm is able to find homogeneous groups, to find clusters, and the result is likely to be something like the one that you see here on the screen. So we are able to color the different observations, defining two groups, group 1 and group 2. The interpretation of the groups will then be the next step. Maybe we discover that group 1 represents those customers that belong to young couples, or group 2 represents a certain type of customer with a given profile, because we are able to complement the information with other type of sources that are within our organization, within our bank. An important characteristic of the k-means algorithm that we have to remember is that when we run the k-means algorithm, the number of groups we will obtain is decided by us. So it's us that will tell to the k-means algorithm, I want 2 groups, I want 3 groups, I want 4 groups, I want 10 groups. So the algorithm will necessarily find the number of groups you have decided at the very beginning. So differently from other clustering techniques in which the number of groups is somehow coming out of the data themselves, in the k-means algorithm, the number of groups is something you decide ex ante. In reality, in next class, we will see that there are techniques that we can use when we have some uncertainty about the possible groups. So if we are not really sure if we need 2 or 3 groups, there are techniques that we can use to try to understand which of the two situations is better from a statistical point of view. In order to cook the k-means recipe, we need 2 basic ingredients, a distance measure and the concept of centroid. Now, in all clustering techniques, distance measures are fundamental. Why? Because we want to actually measure how observations in our dataset are far apart, because we want to group observations that are somehow close in terms of different definitions of closeness that we will see. The concept of centroid is a generalization of the concept of center. Now, in English, the suffix oid means that something looks like something else. So you can see oid as a generalization of something else. In mathematics, we have many oids. We have matrix and matroid. We have graph and graphoid. We have centers and centroids. A distance measure tells us how far apart, how far away 2 or more objects are. Now, in the literature, there are many possible distances that we can use in order to measure the distance between 2 points. For example, we have the Euclidean distance, which is the standard distance we almost use every day in our movements, in our interactions with the environment. But there are also other important distances in the literature. We have the Manhattan distance, the Canberra distance, the binary distance. We can define distances based on the correlation and the different definitions of correlation on the Gini index. So there are a lot of alternatives. And in particular, when we consider clustering techniques, other clustering techniques that are not the k-means, we will see what is the impact of choosing one distance instead of another, because you can really have different results. And the choice of the distance can really be important in terms of the conclusions you can derive from your analysis. Now, also in the k-means algorithm, we will see in the next classes, we can change the type of distance measure we use. But usually, in most applications, the most used distance is the standard Euclidean one, the one that is based on Pythagoras' theorem. Say we have just 2 observations, just to understand what is going on. These observations are characterized by 2 different features, feature x and feature y. Now, if we have just 2 features, the observations can be plotted in a very simple scatter plot as the one that you see here. In this plot, observation 1 is characterized by 2 values x1 and y1, while for what concerns observation 2, we have x2 and y2. Now, using x1, y1 and x2, y2, we can easily compute the Euclidean distance between observation 1 and observation 2. How can we do that? We just use Pythagoras' theorem. So we take the square root of what? Of the distance on the x-axis between observation 2 and observation 1. So x2 minus x1, we square this distance, and we add the same thing done on the y-axis. So y2 minus y1 squared under the square root. That will be the length of the distance between observation 1 and observation 2. The Euclidean distance we have just considered in the two-dimensional case can be naturally generalized to higher dimensions. Now imagine that every observation in our dataset is characterized by m features and that we want to compute the Euclidean distance between observation I and observation j. Okay, the formula that we have to apply is simply the one that you see on your screen. Now, this formula obviously it's a little bit more difficult with respect to the previous one in terms of geometrical interpretation, because when we move to dimensions that are larger than 4, it starts being difficult for our brain to imagine the object. But from a mathematical point of view, it's just a straightforward generalization. So we move to m dimensions. Consider a cloud of points. So we have many points on a plane or in higher dimensions, but let's stick to the two-dimensional case so it's easier to understand. Imagine that we have this cloud of points and we want to compute the centroid that sometimes is also called the geometric center of all the points. Now, the centroid is nothing more than the point that represents the arithmetic mean position of all the other points that we are considering. The computation of the centroid of a cloud of points is a very simple computation. Okay, let's consider the situation that we have on our screens. We have 3 observations. These 3 observations, for example, represent 3 customers. For each customer, we have 2 features, and the 2 features can be represented, as we have already seen, as the coordinates of a plot. Now, we have 3 customers, and these 3 customers have the following value. The first customer is represented by the couple 1, 2, the second customer by the couple 2, 3, and the third customer by the coordinates 3, 0. Now imagine that the first feature is a measure of wealth and the second feature is a measure of, I don't know, some categorical variable representing the characteristic of the customer. Now we have these 3 observations and we are interested in computing the centroid. The first coordinate of the centroid is nothing more than the arithmetic mean of the first coordinates of the different observations. So for us, the first coordinates are 1, 2, and 3. The average of 1, 2, 3 is 2, because we sum them, we divide it by 3, and this is 2. 2 will be the coordinate of the centroid for what concerns the first feature. Now, for what concerns the second coordinate, or that's the same, the second feature, how can we do? It's exactly the same, but we take into consideration the second coordinates of the different observations. So in that situation, we have 2, 3, and 0. So we sum 2 and 3, 5, plus 0, 5. We divide by 3, and what we get is 1.67, more or less. Okay, what do we get? We get this. The centroid of these 3 initial points is a new point whose coordinates are 2 and 1.67. So this is the way in which we compute the centroid of a set of points. If we have hundreds of points, we will have to average much more observations, but this is how it works. And what happens if we are in a multidimensional framework in which each observation has more than 2 features, so say 3, 4, 500. It's exactly the same. The centroid will have exactly the same number of coordinates as the observations, and each coordinate of the centroid will be the average of the coordinates of the initial observations. It's very simple. Now, there is one last thing I want to underline before describing the k-means algorithm, and it's the topic of scaling, which is extremely important for the k-means algorithm and in general for many machine learning algorithms. What is scaling? Scaling is a procedure that we can use in order to make all our features more compatible, more comparable. Why? Because if you consider a standard dataset you might have, it is normal if you're a bank to have features that are expressed in different units. You may have, for example, the income of a customer, and then the income will be something like, I don't know, 50,000 euros, 100,000 euros, 1 million, 3 million, 10 euros. And the range of variation of this feature is very large because of the nature of the feature. Then you consider another feature that represents the age of a customer. Then age, if you are very optimistic, will lie between 0 and 120. And if you have a third feature, the same. Think of, for example, a total different field. Maybe it's not interesting for us as a risk manager, but if you are measuring the length of the distance between two cities, you can express that in terms of kilometers, in terms of meters, in terms of millimeters, whatever you want. And the unit will change the number. Naturally, it's trivial. Now, what happens if we have different features with different scales, with very different scales, because their ranges of variations are very different? The results we might obtain from our algorithms could not be reliable. Why? Because if we have different features with different ranges of variation, what happens is that the feature or the features with the largest ranges of variation will tend to attract more attention. Why? Because the variability they can express is by definition larger than the variability that can be expressed by a feature with a smaller range of variation. Think of something that can move between 0 and 1 million and something that can move between 0 and 3. The range of variation of the first one is very large, so the volatility, the variance, so every measure of variation that we can and dispersion that we may use can be very large. If you are between 0 and 3, the number is relatively small, so it cannot be something comparable. So what we want to avoid is this fact, and scaling is the technique that we can use in order to avoid this. There are different ways in which you can actually scale a feature. We just consider two. One is what we call normalization. The other one is the min-max scaling. Normalization is something that you know for sure from your basic courses in statistics. You take your feature, you remove the mean, and you divide by the standard deviation. If you do that, the new quantity that you get, the new feature, is something that has mean 0 and standard deviation 1. The other approach is, on the contrary, the approach that relies on the minima and the maxima. So you take your feature, you remove the minimum value, and you divide by the range of variation, which is the difference between the maximum value and the minimum value. What you get is a new value, is a new quantity, is a new feature that now lies between 0 and 1. So by doing these sort of scalings, normalization and min-max scaling, we get features that are now comparable, that are compatible in terms of scale. So we remove the problem of this excessive volatility just linked to the fact that the units we use are different. A suggestion is to be consistent. So if you normalize all the features, if you use the min-max scaling, use the min-max scaling for all the features. Again, there are other possibilities, but for us it's more than sufficient to consider these two. And finally, we can describe the k-means algorithm. Now, the first thing that we have to do is to decide how many clusters we want to obtain, because this is our decision. It's not something that comes from the algorithm. Say that we want k groups, so we want to create k different clusters in which we collect our observations. Since we want k groups, we have to define k initial guesses for the centroids. That will be the centers of the k groups. Now, if we start with k different centroids, these centroids can be random, so we just randomly generate a certain number of points in our cloud of points. Then, for every centroid and every observation in a dataset, we compute the Euclidean distance. So if we have 10 centroids and 100 observations, for each of the 100 observations, I will compute the distance with respect to the 10 centroids. After that, I assign the observation to the centroid with respect to which the Euclidean distance is the smallest one. So I start with these 10 centroids, I compute all the distances, and then I say observation 1 belongs to centroid 3 because the distance between observation 1 and centroid 3 is the smallest one. Once I have assigned all the observations to the different centroids, so to the different groups, what can I do? I can recompute the centroids of the new groups that I have identified. If I do that, it's very likely that in the first steps, the centroid will change because the initial value of the centroid was just our guess. So it was nothing particularly related to the data, it was just our guess. Now, when I recompute the centroids, I obtain new centroids. Maybe some remain the same, but some others change. What I have to do is, again, to recompute all the distances from the different observations to the different centroids, and I go in this way over and over again until I reach the situations in which the different centroids no longer move. So it's no longer possible to assign a given observation to a different centroid because every observation belongs to the group whose centroid is the closest one to that observation. Once we obtain this situation, our algorithm stops, and the resulting groups are the groups that our k-means algorithm has discovered for us. Let's consider our first real application using actual data. Everything you need in order to replicate what I'm saying in this video is in the description. In the description, you will find the dataset we are gonna use and the R notebook containing all the transformations, all the steps, the k-means algorithm, and many comments about the different steps. I will show you how to produce different types of graphs using the basic functions in R, but also a little bit more sophisticated things like the ggplot2 package. And I will also ask you to solve some very simple exercise that can be very useful for the next steps in the course, and in particular for the next lessons related to the k-means algorithm. Now, the dataset you find here is part of a real dataset, so these are actual data that was given to me by a large European bank. They were very friendly, very helpful. The only condition was to anonymize a little bit the data so that you cannot understand who a particular customer is. These are actually data belonging to the bank and about a certain number of customers in the very small data set we consider together for this first application, only 72. For each customer, we have a certain number of variables, of features. We have two important features that gives us information about, for example, the expense patterns of every different customer. It's a measure that tells us if the lady behind the little number identifying the customer has a spending pattern that is in line with his or her income or not, or if they prefer to save, these kind of things. Now we have a second feature. The second feature gives us information about the creditworthiness of the customer as estimated by the bank using an internal rating-based model. Now, I do not provide more information about the features because at this stage it's not important. For each customer, we also have another additional piece of information that is in the column default. This is just a dummy variable taking values 0 and 1, and it's a variable that tells us if the customer we are considering in the dataset has defaulted or not. In fact, these data come from a PD study, from a study related to the probability of default. Now, what I want to show you is that even if we ignore the information about the default of the customers, and we just focus our attention on the first two features, so the expense pattern and the creditworthiness, the k-means algorithm is able to recover quite satisfactorily the information about the default. You will see that we are able to find back the information about the default by splitting the customers into two clear groups. Then, analyzing the groups, we will discover that obviously those customers that have a lower creditworthiness and a bad consumption pattern tend to default, and vice versa for the other. But what is important is that actually the k-means algorithm is able to discover a pattern that is not immediately evident in the data if we do not provide the information about the default. So if we consider our 72 customers and we look at the features, they can be represented using the scatter plot that you can see here. As you will see in the notebook in the description of this video, to use the k-means algorithm in R is very simple. There are many different options, but we start from the simplest one. So we use the k-means function in the basic implementation of R without downloading extra packages. Now, this function has several options. In the notebook, you find more details, but the most important information that you have to provide to R in order to perform its task is for sure the data set, so the data that you want to use, and in particular which features you want to use. Not always you have to use all features, as we shall see in the next lessons. The number of clusters that you want to obtain, so the number of centroids you have to start with in order to get the clusters, and a third option that I describe in the notebook in more details, which is the n-start option. Now, that option is important because it allows us to obtain more reliable results. Now, with the small data set we are considering in the exercise is not a big problem. But if you have a very large data set and you want to cluster the observation in, say, 5 groups, what happens? You start with 5 initial guesses for what concerns the centroid, and then you perform the algorithm until you reach the final centroids that do not move. If the data set is very large and maybe you have some problems with the data, so real life is not always as nice as we find in textbooks. It may be the case that the initial points from which you started were not the best ones, and that the centroids that you obtain are actually not the best ones, because they can be linked to a local solution. So in order to avoid this, it is a very nice idea to give R the instruction of performing the k-means algorithm several times with several different initial guesses for the centroids. The n-start option tells that. There are different opinions about how many trials you should perform. I tend to say 30 or more. Other colleagues say that already 20, it's enough. You will see that if you use more initial guesses, then R will select, according to some criteria that we will discuss in the next classes, the best set of clusters, given always the same constraint, the fact that if you start with 10 points, you will get 10 clusters. If you start with 3 points, you will get 3 clusters. So the n-start option does not change the number of clusters you will get. You will always get the same number of clusters. But the stability of the clusters, if you use more trials, improves. Now, as you can see here in the graph, we are actually able, using the k-means algorithm, to cluster our data. How I have obtained this graph and what we can say about this graph, how we can actually give an interpretation to the cluster, is something that you will find in the notebook. So I really hope you enjoyed this second class, and I wait for you in the third one.